Hello everyone. In last video we have seen the design of rigid couplings which are flange couplings. Here we will be studying the design of flexible couplings, and flexible couplings means which are used to connect shaft which are having the misalignment. So these kind of couplings will be permitting some form of misalignment between the shaft even if it is present. So for the perfect example of this flexible coupling is bush and pin type flexible coupling. So this is quite similar to the flange coupling where the bolt is replaced by pins and bush. So here you can see so these are the pin and rubber bush arrangement. So pins, the one end of the pin will be getting inserted or fixed rigidly to one of the flanges, and the other end of the pin is enlarged, and this will be carrying the rubber bush as well as some brass bush lining will also be coming there, and this is getting into this enlarged holes which are larger compared to this holes provided on the other flange. So this is similar to flange coupling, only difference is the bolt are replaced by pin and bush. So it is known as bush and pin type flexible coupling which allows some misalignment. So you can see the diagrams, the detailed drawing showing all dimensions here. And here also we'll be following a similar design procedure similar to the flange couplings. So first we will be seeing the design of shaft, then the size of hub will be found and a suitable key will be selected. The pins which are coming here, the new thing is only this pin and bush. Then finally the flange dimensions will be found, and all these components will be checked whether they are lying in the whether the selected dimensions are satisfying the safety criteria. So first we will be seeing the design of shaft. So design of this all components starting from shaft can be understood with the help of this problem. So here we have a problem to design bushed pin type flexible coupling to connect a pump shaft to a motor transmitting power and RPM is given. So with the help of this one you can evaluate the torque. And here another additional information is given. The overall torque is 20% more. So the torque with which we have to design will be by considering this 20% more, and that calculation is coming. I will be showing the material properties of the different components of this coupling are given. The allowable shear and crushing stress for the shaft and key material is 40 megapascal and 80 megapascal shear and crushing. The allowable shear stress for the cast end, that is the flange material, is 15 megapascal, and the new thing is coming here is the bush or the rubber bush. The allowable bearing pressure for the rubber bush is 0.8 megapascal it is given, and also it is mentioned that material of the pin or you can consider it as bolt, it is similar to that of shaft and the key, same material. So first we will be starting with the design of shaft. You can see the sketch here. So the diameter D, so this is the first dimension that we are finding, and all other parameters like D1, D2, D3 can be expressed in terms of this diameter D. So power is 32 kilowatt, RPM is 960 RPM. So you can evaluate the torque, 318.3 Newton meter you will be getting. And it is mentioned the overall torque is 1.2, 20% greater. That means you can multiply a factor of 1.2, then you will be getting 382 Newton meter. So this is the torque with which all further calculations will be made. And we have to find the diameter of the shaft, for which you will be using the maximum shear stress theory. So maximum shear stress developed the toe which can be equal to allowable shear strength, that is 40 into 10 raised to 6 megapascal equal to 16 T divided by pi d cube. This equation already you are knowing, and we have seen in the last design of coupling also. So this torque you can substitute in as 382 Newton meter. And if you are solving this with the help of proper units, then you will be getting the value as 36.5 mm for the shaft, and we will be standardizing. We will be taking this 40 mm as the required diameter for the shaft. So capital D is equal to 40 mm. So next we will be seeing the design of hub. So we are knowing hub is the portion which is making connection with the shaft with the help of key. So you can see the hub here, this diameter is given by capital D1, and we will be using the same empirical relations used in the last case. That means you can look on to this 13.1 D for hub diameter and this 13.1 G for the hub length. So hub diameter will be equal to capital D1, which is 1.5 D plus 25. Here you will be getting it as 85 mm, and the length of the hub will be equal to 68 mm by substituting these equations. So we have designed the second part also. This is similar to the flange couplings. Next we will be seeing the design of keys. So here keys are used to connect the hub and shaft elements. So here we are knowing the crushing stress for the key material as well as shear stress for the key material is given, which is 40 and 80. So if you are having condition sigma c is equal to 2 times the allowable shear strength for the key material, in such a case we will be selecting the square key. So we have to select a square key for the shaft diameter of 40 mm. So we will be looking onto this table 4.1 to select the suitable key. So shaft diameter is 40 mm, means this is lying in the range of 38 to 44. So in that the key cross section is 12 by 8. So we will be taking the maximum dimension to form the square key. So that we will be selecting the square key of 12 by 12 mm. That means we will be selecting the key with the dimensions 12 mm and h equal to 12 mm. And the length of the key also we have to specify. In the previous step we have obtained the length of the hub portion, that is 68 mm, and that the same will be the length of the key. So the size of the key is 12 by 12 square cross section with a length of 68 mm. So now we have evaluated the dimensions. Next we will be checking for the different stresses induced in this one, and we will be verifying whether it is safe or not. So for checking for the stresses in key, we know the failure of key occurs in two ways. One is due to the shear stress and another one is due to the crushing stress. You are knowing these equations. So all the torque you are having, the length, the B size 12 mm and diameter of the shaft, everything. So this is actually capital D, and this is also, this D is also actually capital D. So from this you can, here you can find the shear stress induced in the key material, and if you are observing, you will be getting the value of the shear stress for the key material is 23.41 megapascal. So this is 23.41 megapascal, and this is well lesser than the allowable shear strength, that is 40 megapascal. So hence this condition is safe. And in a similar way you can evaluate the crushing stress also from here. Sigma c you can evaluate all other dimensions. H is, so this this D is actually capital D, which is equivalent to 40 mm, or in SI units you can convert. H is actually 12 mm and this L is 68 mm. This torque you are already having 382 Newton meter. Then you can evaluate the sigma c value. So then that value will be getting us 46.81 megapascal, which is lesser than the allowable crushing strength of this key material. So here also the key is safe according to both of these failures. So we have designed this element key also. Next we will be seeing the main designing component, which is the design of pins. So in flexible or bush and pin type couplings, the difference with respect to flange coupling comes with the use of this pins. So we are replacing the bolt and by pins. So pin is having some dimension. So here you can see the pin are coming here, over which the rubber bushing is coming here. So that is shown here. So the pin is having some diameter. The diameter is this one. So that diameter will be calling as dp. And here we have to find the three major parameters. One is number of bolt or number of pins. These are actually number of pins, and we will be using the same equation that we have used for evaluating the number of bolt in the case of flange coupling. So here you can see this, you are used this equation 3d by 80 plus 2, and then you will be getting 3.5. then we will be taking the highest even number, which is 4. But in the case of flexible coupling, minimum number of pins required actually in the practical cases are 6. So we will be selecting this number of bolt as 6. So number of bolt is finalized. Next we will be finding the size of the bolt or the size of the pins. So that is represented by this dp. So for finding the size of the pins, you will be using this equation, 0.423 times the shaft diameter, which is 40 mm, divided by root I plus 7.5 mm, that you will be getting as 14.4 mm, which is will be rounded or taken the highest even number as 16 mm. And finally you have to evaluate the pitch circle diameter of the bolt. That means this diameter, the capital D2, you have to evaluate, and for that you are having this empirical relation. The diameter of bolt to circle D2 equal to D1 plus 3.2 times D. Then you will be getting this diameter as 140 mm. So the dimensions of pin we have evaluated. Next we will be finding the dimensions of bush. So bush is the material which is coming as a covering for this pin on the second flange. So here this pin is fixed to this flange, and the other end is enlarged, and on this one the bushes are coming. So usually we'll be using rubber bush with some brass bush lining will be used. So brass will be coming at the inner surface of this pins, and at the outer surface this rubber bush will be coming. So this enlarged portion of this pin and bush arrangement you can see here. And we evaluated already the diameter of this pin DP, we evaluated, which is 16 mm, and then the diameter of this bush, that means this diameter D dash, we have to evaluate. And for this one here we are having equation, diameter of this outer diameter of bush is equal to, this equation is given in data book, I will be showing in the next page, dp plus tr plus tb plus some allowance. So tr is the thickness of the rubber bush and TB is the thickness of brass bush. So here nothing is given, so we will be assuming a value, commonly used values for this thickness. Rubber bush will be of 12 mm and brass bush will be of 4 mm, and a clearance or the misalignment which are permitted is that will be taking us 4 mm. Then you will be getting the outer diameter of rubber bush or the entire bush which is coming over the pin will be equal to 36 mm. So you have evaluated the size of bush also. Next we will be finding the length of this bush required. That means this dimension we will be evaluating. So for evaluating this dimension, that is LB, we are having some equation which is given in 13.5 C, where this torque is equal to this quantity. PB is actually known as the bearing pressure. That is the maximum. This force will be, you can see the force which is transmitted during the power transmission between these flanges, and this will be making some pressure or the distribution of force is actually known as the bearing pressure. And in the question itself it is mentioned that the bearing pressure for the bush material is 0.8 megapascal. That means the value of PB is 0.8 megapascal, or if you are substituting everything in SI unit, then it is equal to 0.8 into 10 raised to 6 newtons per meter square. So all other parameters we are having, I is the number of bolt or pins, D dash is the outer diameter of bush, D2, capital D2 is the pitch circle diameter of pins or bolt, and from this you can evaluate the length of the bush, that is LB. So if you are solving this one, you will be getting the value of approximately 32 mm. So 31.5 something you will be getting, and finally you will be taking the next even or standard number which is 32 mm. So we have evaluated the length of the bush also. Next we will be doing the check for stress in this bush with the help of equations in the data book itself. So we are checking for the stresses induced in the pin or this bush. So first we will be evaluating the shear stress in the pin. For this we will be making use of this equation, the torque capacity based on the shear of bolt. So that is shear of bolt, or it is applicable to our pin also. Then we will be using this equation. So torque you are having 383 Newton meter. So this shear stress we will be evaluating, and we will be making sure whether it is lesser than on the property or the allowable shear strength of the material. So I is the number of pins, dp is the diameter of pin, we will be substituting everything as given, d2 is the pitch circle diameter, and if you are substituting everything properly, then you will be getting the shear stress induced in this pin as 4.5 megapascal, and which is very much lesser than the allowable shear strength of the pin material, that is 40 megapascal. So we are having a condition which is safe. In a similar way, we will be evaluating the bending stress induced in the pins with the help of this equation 13.5 E, and we will be evaluating sigma b as 16 f into L, where this L is actually the LB, length of bush, and all other dimensions pi into dp cube, which is the diameter of pins used. So you will be getting the value of sigma b, and if you are finding this sigma b, this is equal to 42.4 megapascal, and this is very much lesser than the crushing normal stress, that is 80 megapascal. So here also we are having a safe condition. So the dimensions selected are safe. So we'll be proceeding to the design of the next component or the last component in our case, that is the design of flange. So flange you are already knowing. Flange is the element which is getting connected to each other with the help of these pins. So flange is having some dimensions which is known as the outer diameter of the flange D3 and this thickness of the flange T, or here it is mentioned in terms of B. So outer diameter of flange, you can use this equation 13.1 F, that is D3 equal to D1 plus 6 into dp, where dp is the diameter of pin. Then you will be getting a value of 182 mm for this one, and finally you will be evaluating the flange thickness T, or here it is actually small b. Then you will be getting this value as 23 mm, And in the final step we will be making a check for stress induced in this flange also, because the allowable the shear stress of the or shear strength of the flange material was given as 15 megapascal, and this torque capacity based on shear of flange we are actually evaluating this, and from this you can evaluate the toe. And so you can substitute all the known values in proper units, then you will be getting the shear stress induced as 1.46 megapascal for that is the shear stress induced in the flange, and this is very much lesser than the allowable shear strength of the flange material, that is 15 megapascal, which was given in question. So here also we are having a safer condition. So we have designed the different parts or components of this flexible bush and pin type coupling, that is shaft we have designed, hub portion we have evaluated dimensions, keys design, and their stress check for stress is completed, and also the important pin and the bush design is made, and also finally the flange elements dimensions are also evaluated. So this is the complete design procedure for a flexible, and here we have discussed the bush and pin type coupling, which is almost similar to the last one, that is the rigid couplings.